Okay, so in this next video, we're going to look at what happens to elements when they become ions. So remember what we've learned before. Fluorine has 7 valence electrons because there are 2 s electrons in energy level 2 and 5 p electrons in energy level 2 because energy level 2 is the outermost energy level. 2 plus 5 gives you 7 valence electrons. We also know, based on the charge pattern that we learned before, that fluorine being in column 7 means it usually forms a -1 charge. So remember that when something is an anion and it forms a -1 charge, the thing that we are always adding is electrons. We are not changing protons ever when we are talking about things becoming ions. We are changing electrons. So because of that, in the case of fluorine, when it has 1 extra electron, it then has a total of, rather than 9 total electrons, it ends up having 10 total electrons. Okay, so what happens to the electron configuration? It becomes the same as it started, so 1s2, 2s2, and 2p5 then becomes 2p6. Okay, so we've added 1 electron, showing that -1 charge, to the original electron configuration. You'll also notice, hopefully, that when you go from fluorine and you add 1 electron, it now has a configuration like a noble gas. So you could also even write this in shorthand as simply neon in brackets. Okay, so whenever we have things forming ions, they're going to become like noble gases. So looking at sodium, sodium is a metal, whereas fluorine was a nonmetal. Remember, our metals usually form cations, positive charges. Again, we're changing the electrons. So if something has a +1 charge, in order to change the electrons, it's going to give away that electron. So in this case, it's going to give away its 1 valence electron, and it's going to have a configuration with 10 electrons. So it's also going to have a configuration similar to neon. So 1s2, does it look like a 2? 1s2, 2s2, and 2p6. Okay, so in this case, you also could write the shorthand of the sodium ion as neon. Okay, so basically what we're seeing here is that the electron configuration alone, 1s2, 2s2, 2p6, if you know that it's neutral, that's the configuration for neon. But it can also represent an ion with a -1 charge or an ion with a +1 charge. Notice over here as well, by the same token, if we look at oxygen, oxygen is in the -2 column of ions. So when it forms that -2 charge, it gains 2 electrons and also has a configuration like neon. Magnesium is in the +2 column, which means it gives away 2 electrons. So magnesium giving away 2 electrons is also like neon. So anything that's going to form an ion that ends up having 10 electrons total will have the same overall electron configuration. All right, let's look at iron, which is a transition metal. So iron being right here, remember we have the 4s electrons, but then the d energy level is actually an energy level lower than the row it's in. So this is 3d on the top row of the d block. So our configuration ends with 4s2, 3d6 being our leftover electrons if we're talking shorthand. Remember, it's the 4s electrons, or the 2 electrons in energy level 4s, that are your official valence electrons. So typically, iron can form a +2 charge by losing those 2 electrons. Okay, that means that your shorthand, just for sake of time, is going to be argon with only 3d6 left over. Okay, so that iron should have a total of 26 electrons when neutral. If it forms a +2 charge, it should have 24 electrons. So to double check that, you can say argon, which is 18, +6 gives you 24, which makes sense for the number of electrons you would have in a +2 iron cation. Additionally, because transition metals are weird and annoying, you also can have them form other charges. So that's why you always have to indicate their charges with the Roman numerals in their names. So the way you can have iron form a +3 charge is now if it loses one more of those electrons from that D sublevel. So now we have a total of 23 electrons versus our neutral 26, giving us a +3 charge and a configuration of argon with 3d5. We'll see more why 3d5 is stable in just a second. Okay, so now I'd like to talk about exceptions to what we know about transition metals. So using our example from iron before, I'd now like you to write out the longhand and the shorthand configurations for both chromium and for copper. So please pause the video, write out the longhand and shorthand for both of those elements, and I'll wait. So based on what you've learned thus far, you would have written out your configurations like this. So your noble gas for your shorthand is going to be argon for both of these, and chromium would end with 4s2, 3d4, whereas copper is argon 4s2, 3d9. So if we were showing the electron diagrams or the orbital diagrams for this using shorthand to save time, we'd be labeling the 4s sublevel and the 3d sublevel. Remembering our rule of SPDF 1357, that's why the D sublevel here has 5 boxes. Okay, so if we were drawing our orbital diagram, we would show our 2 electrons in the S sublevel and our 4 electrons in the D sublevel are going to be all separately shown with 1 orbital empty. Unfortunately for you, everything that you know about these 2 elements is actually incorrect. Then let's look at what really happens. So we still have our correct number of electrons. So this is still going to be chromium down here. Okay. So based on what we drew before, we had chromium with the 4s2 3d4. Okay. Unfortunately for us, as far as chemistry goes, all things have exceptions. In this case, it's actually way more energetically stable for that S electron here to jump over to this orbital over here so that our D orbital is half filled. So 3d5 is really stable. 3d4 having this empty spot is not so stable. This is only true when you have either 3d4 or, as we'll see, also 3d9. Okay, so if you have 2 empty spots, it's just 3d3. It has to deal with having 2 empty orbitals. But if you only have 1 empty orbital here, this 1 electron will jump over, and we'll see that it's going to change what our orbital diagram and everything else looks like. So if we draw this with that electron shown, so if we have chromium with argon, okay, so if we show that electron moving, we'll have 1 electron in every single orbital. Okay, so if we were writing out the longhand for that, we would write out all the configuration for argon. I'm going to skip over that, but I will write out the end after argon. It's going to be 4s1, 3d5. So 4s2, 3d4 from this point forward is not a correct configuration for chromium. 4s1, 3d5 is, because this is going to show that that 1 s electron from 4s jumped up to fill in that empty d orbital in 3d. Okay, technically this is true for any of the elements in the same column as chromium, but the main examples I want you to know are chromium, copper, and I'll show you silver as well. Okay, so by the same kind of logic, if we were writing out copper's configuration and orbital diagram, remember we originally wrote that that was 4s2 3d9. So the same thing is going to happen where you're going to have 1 electron take the extra spot. Okay, so when we had 9 electrons here, we had them all filled in except for there was 1 unpaired electron out here. our S electron is going to jump up here, and this is the most stable configuration for copper. Okay, so this case it would be 4s1, 3d10. So it's by the same logic as chromium. So as one last mind-blowing thing, remember when we learned our elements that have fixed charges, and we remembered these 4 elements had specific charges all the time. If you apply the same thing that we talked about with copper to its row, or to its column, including silver, if we write out the configuration for silver, we would see that it can be abbreviated by krypton, our noble gas-rich friend that's going to give us a ride. And then we would have, in this case, our next row after krypton is going to be 5s2, 4d9. But by the same logic as copper, it's going to be 5s1, 4d10. And so if we're analyzing this for number of valence electrons, there is only one valence electron. And if you remember back to when we labeled our fixed charges, silver we remembered is always +1, and this is why.